Welcome, everyone, to the final session of Statistical Thinking for Forensic Practitioners, a CSAFE Fall 2022 short course sponsored by NIST. Your speaker today, back for the final round, is Hal Stern, the Provost and Executive Vice Chancellor and Chancellor's Professor in the Department of Statistics at the University of California, Irvine, the Co-Director at the Center for Statistics and Applications in Forensic Evidence, CSAFE, and a 1 in a million educator, not just for future statisticians, but for you. Hal, it's yours for the final session.
Great. Appreciate the introduction, Anthony. It's really great to be back for the fourth and final session of Statistical Thinking for Forensic Practitioners. I'll remind you the outline for the entire short course. So we started, I guess it's formally 3 weeks ago, with a discussion of probability and talked about Bayes' theorem. That will come back today. In part 2 weeks ago, we talked about collecting data, reliability, validity, and forensic evidence evaluation as expert opinion. That is, we had a chance to discuss black box studies and some of the measures that they provide. Last week, introduced the concepts behind statistical inference, which are very closely related to what is known as the two-stage approach for assessing forensic evidence. And today, the final session is on the likelihood ratio approach to assessing forensic evidence. I worry a little bit in the sense that the outline seems like it's all leading up to the likelihood ratio approach, and that's everyone should do that. And there's an element of truth in that. I do believe the likelihood ratio approach is extremely important and compelling way to think about evidence. But I hope that the first 3 weeks have also proven useful with useful tools and useful ways of thinking. So the goals for today are to understand, hopefully, the ideas that lie underneath the likelihood ratio. And then we'll demonstrate how the likelihood ratio approach works, first for categorical evidence, and that's the place where I think it's most easy to grab onto the ideas, and I hope that will be true for you. And then to think about how it can apply in other types of evidence, especially pattern evidence, as CSAFE is a NIST-funded center of excellence with a focus on pattern evidence. And then throughout to understand the strength and weaknesses of the likelihood ratio approach, probably better framed as the strengths and challenges of using the likelihood ratio approach. The first third or so of the day today is really kind of a review that is, in some instances, exact same slides as we saw in a previous week, to bring some ideas back to the front of the story, hopefully to the front of your minds. And so probability plays a key role, has played a key role throughout the short course, and plays a key role in today's discussion. So here's a few of the key bullets about probability. Numbers between 0 and 1 describing the chance an event will occur. And I guess 2 key things on this first slide. One is conditional probability turns out to be a key event. And the way the conditional probability works is we talk about assigning probability to some event A, given that we have some information B that we know to be true. And this notation and the ideas behind conditional probability can be confusing. And so we have to make sure to be cognizant of the role of the 2 events here. One event, the A, is something we are assigning probability to. So that could be, what is the probability that a randomly chosen person has blood type A, and B is some information we're assuming to be true. And so that could be, and will often be today, B will be something like the 2 samples have the same source, or the 2 samples have different sources. So we'll emphasize that as we go through. Whoops. Make sure I didn't skip one there. Sorry. The second review slide is for part 2 of the course, where we talked about collecting data to learn from a population, and talked about the key role of randomness in being able to generate a representative sample. We also talked about when we take measurements on our samples, the importance of accounting for uncertainty. So in any measurement process we take, measure your child's height, measure your own weight, and you measure it twice, you get slightly different answers. That's what I talk about uncertainty. That's the uncertainty associated with a measurement. Uncertainty is also associated with decisions. So in my view of the world, a decision is just a measurement, right? Given this evidence, I make a determination as to whether I believe these are same source or not. That's a decision or a measurement. And the black box studies that we talked about are ways of assessing the reliability or consistency of those decisions. Will I make the same decision given the same evidence? And validity refers to the accuracy. Does my decision match some ground truth? And so we spent some time talking about black box studies. And one of the things I will do today is use some black box data to connect with likelihood ratios. The other part of our data discussion was to talk about the different kinds of data. This will be important today because the data are ways of summarizing evidence, and the likelihood ratio will call on us to understand how likely different kinds of data is, how likely different blood types are, how likely different consecutive matching Shreya assessments are for bullet data, how likely different measures of refractive index for glass samples. And probability distributions are a concept we introduced only very briefly during week 2. But the role that they play gets much more important today. Probability distributions are used to describe how likely we are to see different values. And so we'll see them show up. And then the third piece of the short course focused on statistical inference, where I'll remind you, statistical inference is the term we use to describe how sample data can allow us to draw conclusions about a population. And we talked about estimation and confidence intervals and hypothesis test as the main tools. And spent a lot of time talking about hypothesis tests because they are critical to what's known as the two-stage approach to forensic inference. We demonstrated that with glass data. So we have glass fragments from a crime scene, glass fragments from a suspect. And the two-stage approach at the first stage says, are these two samples indistinguishable or not, or can they be distinguished? And I tried to argue last week that that's essentially a statistical inference question that I would translate as, do these two samples come from the same population? Or if we think about them as potentially two different populations, do those two populations have the same mean, in which case I won't be able to distinguish them. And so that led us to a statistical test. And then the second stage attempted to quantify, if I found the indistinguishability, if I found the two samples were indistinguishable, how likely is that to occur by chance? So that was the second stage. And what we will see today is that the likelihood ratio is closely related to the black box study and to the two-stage approach. So with that as the review, let me pause for a second to reinforce a couple of things that Anthony said at the start, one of which is we'll have some Zoom polls in a little while. Encourage you to participate in those. Also, please ask questions. The Q&A, I monitor the Q&A throughout. If you type a question in, I will look for an opportunity to break. There are various places during the presentation where I can easily break and go back and ask questions. Instructors, including me today, we really like questions because though I like to think I'm clear and do a good job explaining, it's never completely clear. And if you are confused, I can guarantee you that others are confused. And if we share our confusion, we can maybe work through it. So a plea for questions and a plea for participation. Now back to our regularly scheduled program. The slides I'm about to show you, we have looked at each of the last 2 weeks, so I won't spend a lot of time on them. This is just kind of a discussion that says lots of forensic questions, but we're going to focus on the source conclusion question. Do two objects or items one found at the crime scene, one on the suspect, have the same source or not. We summarize that question by identifying two hypotheses, one here labeled H sub S, which is that items from the crime scene and suspect have the same source, typically meaning the suspect is the source of the crime scene evidence, and H sub D, the different source hypothesis, that is, these two items, even if they look similar, actually came from different sources. And the goal is to assess the evidence and make some determination about whether we believe the common source or specific source hypothesis, same source hypothesis, or the different source. The way that we do this is we look at the evidence, and I use the evidence in a couple of different ways. We can think about the evidence as the items that we've collected, that is the footwear impression and the shoe. I will frequently today be thinking about the evidence as the measurements we derive from those items. And so they could be glass measurements, they could be images of a shoe impression and test impression from a shoe that we have. Right? And then we want to look at these at the evidence and identify similarities and differences. How close are the measurements or how similar are the images, and also look for differences, and then ask how likely we are to see the similarities and differences under the same source hypothesis. Any differences we see would have to be explainable by, say, distortion in fingerprints to believe the same source hypothesis. And we also assess the observed similarities and differences to see if it's more like what we would expect under the different source hypothesis. And we have spent the last 2 weeks I tend to break down the various approaches to forensic and evidence analysis into these three broad categories: expert opinion, two-stage approach, likelihood ratio. And so last 2 weeks we spent on the first two, today the third, and with that all as precursor, off we go. I start the likelihood ratio discussion today by reminding you of a case we discussed, for those who have been here throughout, on week 1 of the course, the state of Connecticut versus Skipper. This was a sexual assault case in which the man was accused of sexual assault. A child was alleged to be the result of that assault. And so there was a paternity test done to see if the suspect was plausibly the father of the child. And there was an expert witness from one of the genotyping firms. They testified that there was a paternity index, which is a likelihood ratio, we'll explain in more detail, of 3,496. And the expert went on to say, not only is there this likely ratio, which can help us in this case, but I can do more and help the jury by turning this likely ratio into a probability of paternity. And he did that and reported the probability of paternity at 0.9997. That is a 99.97% chance that this was the father. And here's the way that the likely ratio shows up in this case and what the expert was really saying. E in this case is the genetic evidence. There's evidence of the woman who was assaulted, genetic evidence of the child, and genetic evidence from the suspect. And there are two hypotheses. In this case, I changed my letters a little bit because it's not a same source question. HD is that the defendant is the father, and HR is that the random man is the father. And Bayes' theorem, which I will show you in a second in more detail, provides a way of going from hypotheses, probabilities about these hypotheses, through the evidence to posterior probabilities. The expert testified that the evidence we have, these genotype measures, these genetic data measures, are 3,500 more times more likely if the defendant is the father than if a random man is father. That is, the defendant's genes match closely to the data, and the data are much more likely under that hypothesis. To turn this into a posterior probability, the expert assumed a priori that the two hypotheses were equally likely. Skipper appealed, he was convicted, appealed the conviction. And you may remember the state Supreme Court in this case actually upheld the appeal and remanded for a new trial. And the reason that it did so was the court said the only way for the expert to go from the likelihood ratio to the posterior probability was to assume that the defendant had a 50% chance of being the father as a starting point. And the judge felt that this violated the presumption of innocence and set it back for a new trial. So that's a very quick review for those who were here, not critical for those who were not. But what is critical is I'm going to now go through Bayes' theorem. And so again, the slides you're about to see are repeats from week 1. And I find it helpful, and hope that you do as well, to learn about Bayes' theorem by thinking about a diagnostic test. The setup here is a diagnostic test for gunshot residue, but it also works as a pregnancy test or a drug test. And so what happens is there's a little table here that we call a 2x2 table because there are 2 rows. The rows in this case correspond to the ground truth. In this case, the first row says, G, gunshot residue is truly present on the sample, and not G is there is no gunshot residue on this person's hands. And then the columns correspond to the test result. So we have a test that takes a swab from the hand and assesses it for the presence of gunshot residue. The test also has 2 possible outcomes. T, the test is positive, or not T, the test is negative. And if the 2x2 table then gives us 4 situations, this top left is the subject does have gunshot residue on their hand and the test comes back positive. That's a true positive. And then there's a false negative. That is, if the suspect has gunshot residue on their hand, but the test comes back negative, that's an error. It's a false negative error. And so, and then similarly for the cases where there is no gunshot residue, we can get true negatives or false positives. So, and these are typically summarized this way. So this is our first instance in the day of looking at a conditional probability. The first row where my cursor is here says the probability that the test comes back positive, given that I am in the world where the person actually has gunshot residue. This is known as the true positive rate or the sensitivity of the test. And then we can also look at the specificity of the test or the true negative rate, which is when I apply the test to people who don't have gunshot residue, how often does it correctly tell me they don't have gunshot residue? That's how specific the test is. And then the errors are the others, the false positive and the false negative. So Bayes' theorem is a way of taking information we have about the test. We know the sensitivity and the specificity of the test, and it allows us to turn it around and say, I've now got a positive test result. How confident can I be in that test result? And this is the part where, statistics doesn't match how a lot of people's intuition works, right? Our intuition would be, oh, the test came back positive. There's gunshot residue here. But statisticians, and hopefully all of you, have now understand that it's important to think about the uncertainty. The test is a measurement. It came back positive, but there's some chance that it's incorrect. There's always some chance, hopefully small, that the test is incorrect. It turns out to do that, Bayes' theorem requires one more piece of information. It requires some information, sometimes called prior information, about the prevalence of gunshot residue in the population of interest, or the prevalence of the condition that we're testing for. So if it's a pregnancy test, it's how often are people who do pregnancy tests actually pregnant. If it's a drug test, it's how often is this population that I'm testing actually have use drugs. The prior information turns out to be important. We'll see that in a minute. And so again, repeating examples we saw, here's a situation. Suppose I have what I would consider to be a good test, not a great test, I must confess, it's a good test, but it's not a great test. The test is very sensitive. If you have gunshot residue on your hands, the test will come back positive 98% of the time. If you do not have gunshot residue, the test will come back accurate 96% of the time. It will correctly come back negative. And now, to show you how this works, Bayes' theorem works, I'm going to assume for the moment that we're operating in a population where gunshot residue is fairly common. So that I know, in my mind, I think, okay, we're in the West here, we're in Wyoming. Okay, we test an individual and get a positive test result. What can we say about the probability that the individual actually does have gunshot residue on them? The test says they do. What do we know about whether they do or not? And I put here the answer. It turns out that we're very confident that they do, 99.5%. But you may remember my tree diagrams. The easiest way to understand how this world is working, how this probability and statistics world is working, is to imagine applying the test to 1,000 people that we randomly pick from the state of Wyoming. So this is just a conceptual picture about how to think about probability. Probabilities are basically frequencies. So let's imagine we have 1,000 people. And if I drew them from a population we'll call quote unquote Wyoming, that has a lot of people who fire guns as a hobby and in hunting, then maybe 90% of those people, or 900, have gunshot residue on their hands, and 10% or 100 people don't. Let's use our test on these people. The people who have gunshot residue, remember the test is very accurate. 98% of them come back positive. That turns out to be 882 people. 2%, we make a mistake. The test makes a mistake. 18 people have gunshot residue, but the test comes back negative. And now let's move on to the 100 people that do not have gunshot residue on their hands in this sample. Again, the test is accurate, and 96% of them are found not to have gunshot residue, but 4 of them return a false positive. And so probability is about frequencies. We already use some of the probabilities to say, if I know that people have gunshot residue, how many of them is my test going to find? And now I'm going to flip it, and I'm going to ask the question, now I know I got a positive test. How many people did I get a positive test, and how many of them actually have gunshot residue? You can see the paths marked in red here. Those are the people who tested positive. A total of 886 of the 1,000, and 882 of them are true positives, which gives me 882 divided by 886, or 99.5% chance that the test that came back positive is in fact accurately reporting the status of the individual. Perfect. Last piece of this story. So the first 5 lines here repeat what we just went through. And in the past, I asked you this as a Zoom question. Today, I'm just telling you, if I repeat that example and I make only one change, I do the experiment, not in Wyoming, where gunshots are common, or where people shooting guns is common, but to another place, maybe Connecticut, where it's less common. So now assume most people in this population do not have gunshot residue. Only about 5% do. And now we get back a positive test. It turns out Bayes' theorem now gives us a different answer, and I think a shocking answer. The test came back positive, but now the probability that the person actually has gunshot residue was only 0.56. So I'm not going to go through it in detail. We have lots of other things to cover today, but the prior probability, the prevalence, played a big role. Because so few people have gunshot residue and so many don't, the false positives begin to play a bigger role, and I'm less confident when I get that decision. So the role of prior information is important, and sometimes when you hear people concerned about reporting posterior probabilities or probabilities about hypotheses, it's because of the role that prior information plays, as in the Skipper case. So how is this going to work for us today? Today, we're going to apply the same idea, not to gunshot residue test, but really to forensic examinations. And so E will be evidence. And again, I'm going to work through 3 examples, and those are referenced here. The first is DNA. The second is glass fragments. The third is some kind of pattern evidence. So here I mentioned bullet cartridge images. We have these 2 propositions, same source, different source. And then as what was the diagnostic test result given truth, and truth given test result now looks this way. We will want to talk about the probability of seeing certain evidence under the same source hypothesis and the probability of seeing certain evidence under the different source hypothesis. So I can think about this in terms of the previous example as the probability of getting a certain test result, that's the evidence, given the true status of an individual, that's the hypothesis. Does the suspect have gunshot residue on them? And we can also talk about the flip of those probabilities, that is the other direction, to say, what's the probability that the suspect is the source given the evidence? And what's the probability the suspect is not the source given the evidence? So these are analogous to being able to say, now that I got the test result, what can I say about the individual? So second time I'm going to say it today, but not the last. When we write things this way, we're talking about what are we assigning probability to? So up here, we're assigning probability to seeing this type of evidence. And what are we assuming we know? In this case, we're assuming we know it's a known match or a known non-match, and asking how likely we are to see different types of evidence. And on the bottom of this slide, we're asking the opposite question. Given the measurements I've made, what can I say about the hypothesis? So that's repeated here. When you teach, you don't like to say things are confusing because the whole point of teaching is to not make things confusing. But to be sure, it's easy to see how individuals get confused because these 2 probabilities look so similar. There is a lot of confusion when people do studies with individuals with potential jurors. There can be a lot of confusion. I'm not going to belabor that here. We'll see it more as we go forward. So now let's jump. That first 30 minutes today is review, and let's use that as a launching pad to a conversation about the likelihood ratio as an approach to assessing forensic evidence. And the setting that I think about here, and invite you to think about as well as we go through the various examples, is the trier of fact, we can for shorthand say the jury, is really being presented typically with a suspect and 2 hypotheses. The prosecution often saying the suspect is the source of a certain type of evidence that was found at the crime scene, and the defense saying not so, some other person left that evidence. The jury's job is to make a determination about whether the suspect is the source or not. So they are definitely trying to make a decision about the true state of the world, given the data that is presented in court. So there's no dispute in that. The challenge that we have is that what we know how to do, as in the gunshot residue test, is we know how to make statements about how likely the evidence is given the hypothesis. And we want to be able to inform the jury who's interested in the opposite probability. We just saw that Bayes' rule is a way of doing this. Bayes' rule is a way of going from statements about the likelihood of the evidence given the hypothesis and turning them around to likelihood of the hypothesis given the evidence. And so Bayes' rule is one of the reasons that a lot of attention gets focused on the likelihood ratio. We did see this information back in week 1, but now that we've spent a lot more time thinking about statistics and forensics, it's valuable to look at it again. And so E evidence, H sub S, the same source hypothesis, H sub D, the different source hypothesis. Bayes' theorem, which I showed you in a tree diagram a few minutes ago, can be written in this form. And this is the form for the day. There are 3 ratios here. A ratio is one number divided by a second number. There are 3 ratios here. The first ratio on the far right is the prior odds. It is the probability of same source hypothesis being true divided by the probability of the different source being true a priori, before seeing any evidence. The middle term is known as the likelihood ratio. It looks at the probability of seeing evidence like the type I have in this case under the same source hypothesis, assuming the same source hypothesis is true, and relates that or looks at the relative size of that compared to the probability of seeing this evidence under the different source hypothesis. And what the Bayes' theorem tells us is a mathematical result. It says if you have a prior opinion and you combine it with the likelihood ratio, you get out at the end of the day by multiplication the posterior odds. The left-hand side is, and as I say, I think we all agree, the left-hand side is what the jury needs to be thinking about. Having seen this evidence, how likely do I think it is that the suspect was the source of that evidence? So the likelihood ratio is this middle piece, and the argument I'm going to make, and it's not unique to forensics, it comes up in other fields as well, is that this is the place where the science lives. The science can tell us about how likely we are to see certain types of evidence given different hypotheses, and that the prior odds and the posterior odds are the prior odds involve subjectivity at a very high level. That is the only way to get them. A couple of notes. Likelihood ratio, as I said, not unique to forensic, comes up all the time in statistics and statistical applications. So we talked about diagnostic tests. Very common for people to talk about likelihood ratios in diagnostic tests. It's how doctors move from hypothesis about what disease you have, which would be like the prior odds. You walk into your doctor's office with a sore throat, and then the doctor starts asking you questions. They start gathering evidence, and then they update their opinion about what disease you likely have. Right? And so typically these days, people come in with a sore throat, and the doctor says, oh, let me give you a COVID test. Let's see if it's COVID or not, right? And then the COVID test comes back and they update and they say, I think you have COVID. You should go home and isolate for 5 days or 10 days or whatever. As many of you will know, Europe has moved in the direction of supporting a likelihood ratio as the appropriate summary of the evidence. So we'll come back to that towards the end. Whoops. So a few more discussion slides about the likelihood ratio before we leap into examples. The likelihood ratio is about the likelihood of the evidence under the 2 hypotheses. It's assigning, both the numerator and the denominator here are assigning what is the probability of seeing evidence like this. So they are not making statements about whether it's same source or not. They're making statements about the evidence. So let's talk about the 2 pieces. The numerator first. The numerator assumes that we have the same source for the 2 evidence samples and asks how likely we are to get these 2 evidence samples in that case. If the evidence contains many similarities and no major dissimilarities, if we're looking at 2 fingerprints and we see lots of matching minutia and no conflicting minutia, then we might decide that our assessment is the probability of seeing evidence like this under the same source hypothesis is quite high. If, however, the two fingerprints start off with different patterns, one's a loop and one's a whirl, we might say these could not possibly have come, right? And then we'd say the probability of seeing one impression have a whirl and one have a loop, if they came from the same source, is extremely low. I'll note that this piece of the likely ratio is actually quite similar to some of the things we did last week when we looked at testing hypotheses. We in the testing, well, we said, let's assume the null hypothesis is true, that these two populations are the same, and let's ask how likely it is to get measurements like this if they are. We called that the p-value. And a low p-value was essentially a way of saying, I'm not likely to see measurements like this if they come from the same population. And so we kind of reject HS. So there is a connection here. We're trying to assess how likely the evidence is. But one of the things I like about the likely ratio is it does not, at this early stage, require a binary decision to say, yes, they match, no, they don't. It just is a quantification of how similar the evidence is. The denominator, of course, is the opposite scenario. How likely is it to get evidence like this if the two samples came from different sources? If the evidence contains many, many similarities, if you do a genetic analysis, as in the Skipper case, and you find all of the suspect's genes are consistent with being the father of the child, then you would say the probability of getting evidence like that, if the defendant is telling the truth and he's not the father, is very low. But if instead there were a lot of differences, we would say, oh, this is consistent with the notion that this is in fact not the father, that someone else must be the father, right? So again, we try to quantify that. And once again, what I like about it is this relates to the second stage of the two-stage approach. It says, suppose the alternative is true. Suppose the defendant is telling the truth. Then what's the probability of seeing, the evidence that I have here? In the two-stage approach, we asked, what's the probability of seeing a match? Because the analysis would have ended if there were no match. But we've seen a match. So now let's do that denominator calculation and find out how unusual it is. But once again, we don't rely on a binary decision. So that's what the likely ratio is about. This is the fine print, the end user license agreement. Some of the details on why we call it a likelihood. Some of you may have heard people talk about Bayes factors. Turns out the likelihood ratio and the Bayes factor are, in one sense, the same exact thing. There are subtle differences between them. They are subtle differences that, in my opinion, are much more important to statisticians than to forensic practitioners. So we won't talk about them. So for today, the likelihood ratio and the Bayes factor are the same. So as Anthony mentioned, we have some Zoom polls. So I'm going to get to the first of those in a minute. How do we use the likelihood ratio? The likelihood ratio is basically comparing two probabilities. One, how likely the evidence is under the same source hypothesis, the other under the different source hypothesis. If the likelihood ratio is greater than 1, it means the numerator is bigger than the denominator. It means that the evidence is more likely to be obtained under the same source hypothesis. If the likelihood ratio is less than 1, means the numerator is smaller than the denominator. The evidence is more likely under the defense hypothesis or the different source hypothesis. And if the likelihood ratio is 1, it means the evidence is equally likely and so truly not informative. A couple of final comments. We tend to write the likelihood ratio in this way, same source over different source, but we could flip it. It would just change the interpretation, right? So it's most important just to understand what are the two probabilities, which is bigger. The way that we use the likelihood ratio, as we did in the Skipper case, is we say the evidence in this, in that case, the genetic evidence is likelihood ratio times more likely, 3,500 times more likely, if the father was the suspect, if the objects are the same source, than if the objects have different sources. The challenge for the likelihood ratio is it has its uncertainty in it. That is, there's no rule for saying, oh, the likelihood ratio of 100 is conclusive, but 99 is not. So the European group actually has mapped likelihood ratios to a verbal scale, or includes that as an option. And I'll show you more about that later. But so that's how the likelihood ratio gets used. So let's review with a couple of questions. Here I ask what the numerator of the likelihood ratio means, and I believe it's set up so that you can answer, so check any answer that you believe is true. So here, the large number of people, some people clicked more than one, but the large number of people picked the third one down. Some like the fourth one. And so let's go through those in a little bit more detail. Thank you to the 38 people who participated, which is almost everyone, but we can do better on the next question, coming soon. So very few people picked the first two, and that's good because they're not correct, right? That is, we know we can't really say the probability the suspect committed the crime. The second one says the expert witness trying to confuse the jury. They're probably not trying to, although they may be successful anyway. The last two are really the ones we want to talk through. The third one, which the large majority of you identified, says, what's the probability of seeing evidence like this if the two samples came from the same source? That is the correct answer. And the fourth one, which was the other one that about a third of the people chose, says, what's the probability the two samples came from the same source, given the observed evidence? Is the, as I say, incorrect here, but a common misunderstanding. So strongly encourage us to think about what are we assigning probability to? Here we are assigning probability to observing evidence like the evidence in the case. In this second sentence, why do I say it's incorrect? This is assigning probability to the two samples came from the same source. What I've tried to argue is that can't be done without starting with a prior opinion about that. And we don't want to do that, as the judge in the Connecticut case said, because we that goes against the presumption of innocence, and we don't really have a basis for that. So we want to only focus in on how likely are we to see evidence like this. Now, clear and move on. Okay. Second question. There's always a chance to makeup question. Let's ask the same thing about the denominator. What is the denominator measure? So these statements are exactly parallel to the previous. And so again, the third is the statement that talks about the probability of observing certain types of evidence. And the fourth, which is not correct for interpreting likelihood ratios, because it focuses on the hypothesis and not the evidence. So the remainder of the time we have today is an example that I sometimes facetiously call the good, the bad, and the ugly. And that's kind of harsh. I borrow that from the famous NIST fingerprint data set. But we go through some examples where it's clear how it works. And then I have a second example where you can see how it could be done, though there are more challenges. And then we get to the pattern evidence world, which is where CSAFE has been trying to do its work, where it's especially challenging. So let's start with the nicest case, where the data is categorical, blood type in this case. Suppose we have evidence for a crime scene sample, we'll call that Y, and a suspect sample, we'll call that X. The source of the suspect sample is known. It came from the suspect. The source of the crime scene sample is unknown. It's random. We think it may have come from the suspect, but we're not 100% sure. And so that's the place where the probability needs to live. It needs to live in what can we say about why. And I'm providing here some background information about blood types. And suppose both samples are type O. That is, we found blood at the crime scene, it is type O. We have a suspect, he or she is also type O. And the likelihood ratio tells us if we want to assess the evidence, we should ask the likelihood of observing O for both X and Y under the two hypotheses. Now, it turns out in this case, there's no randomness with the suspect. The suspect's type O. No uncertainty associated there, other than that the test may not be a perfect blood typing test. But that's pretty small. So the way I frame this is, what's the probability that the crime scene sample would be type O under the two hypotheses? So the first thing, the numerator, we say, what's the probability that the crime scene sample is type O given two pieces of information? The suspect is type O, and the suspect left the sample at the crime scene. Well, if the suspect left the blood at the crime scene, then the probability of matching blood types should essentially be 1. The little squiggly lines are, it's not quite 1 because there could be contamination, there could be a problem with the test, right? But it's pretty close to 1. The denominator is the alternative different source world. And it says, what's the probability that the crime scene sample would be O? Since if I know the suspect is type O, and I know the suspect didn't leave it. Well, if the suspect didn't leave it, the fact that the suspect is type O is is irrelevant. And so all I really need to know for the denominator is, how likely is it that a random person that left that blood scene, the other person, was type O? And to start with, I'm assuming I don't know anything about that person, so they must just be a random US person. And 44% of those US people are type O. So in the denominator world, there's a 44% chance of seeing a type O blood. So the likelihood ratio then would be 1, the likelihood of seeing matching blood types in the same source hypothesis, divided by 0.44, the probability of seeing different blood type, seeing the same blood type under the different source hypothesis, which is 2.3. So the same source is more likely, the evidence is more likely under the same source hypothesis. By the way, you can see how confusing it is because I often start saying it the wrong way. But 2.3 is not very large. So we would think about this, if you will, as weak support for the same source hypothesis. And I make a couple of notes about how this can work in other cases. If it turns out that the blood type of the suspect doesn't match the crime scene, then the numerator will be very small. And so we will say the blood type evidence is much more likely under the different source hypothesis. But note also, if they do match, but they match on a different blood type that's rare, AB in this case is the rarest one, the likelihood ratio would change. The likelihood ratio would now be 1 divided by 0.04, which would be 25. And so here you have this feature of the likelihood ratio that matches the two-stage approach, that we have to ask, how rare is the matching evidence? And so finding matching blood type AB is actually stronger evidence about a suspect than finding matching blood type O. So that to me is the simplest example. Closely related to that is DNA. The way that DNA works, if you have not read or recall your biology, is at every location on the genome, you have alleles corresponding to that site. And the alleles are typically identified with numbers or some other approach. And so this is a specific location along the genome identified as TH01. There are a lot of different alleles. You could have a 4, a 5, a 6, a 7, an 8, a 9, a 9.3, a 10, or 11. So those are different alleles in the population. Every individual has 2. You get one from mom, you get one from dad. And like blood type here, the situation is I see 2 alleles on the sample found at the crime scene. I can identify the 2 alleles in the suspect's sample. In this case, the two alleles are a 7 and a 9. I'm not going to teach you the biology, but the biology of it is that the way that you get your alleles is there's a 16% chance that you end up with a 7 and a 20% chance that you end up with a 9. So that gives me 0.16 times 0.20, but there are actually two ways that could happen. You could get the 0.16 from your mom and the 0.20 from your dad, or vice versa. And so the overall probability of a single individual getting a 7 and a 9 turns out to be 0.064. The likelihood ratio, just based on this one spot on the genome, is 1 divided by 0.064, or 15. So this is something like a rare blood type. Matching at one location on the genome gives you a likelihood ratio of about 15 here. But of course, we don't do DNA analysis at just one spot. CODIS used 13 locations before 2017 and more now. I don't remember what the number is now, 20, 21, whatever. And it turns out there are a couple of other pieces that make the likelihood ratio interesting in the biology here. Different chromosomes are independent. And way back in week 1 of the course, we learned that if events are independent, you can multiply probabilities. Multiplying probabilities in this case is the same thing as multiplying likelihood ratios, which means you can imagine if you had 13 locations and each of them gave you a number on the order of 15, 10 or 15, you get 10 times 10 times 10 times 10 times 10 times 10, et cetera, et cetera. Extremely large likelihood ratios. And so we've all heard and seen numbers that say the evidence is 2 billion times more likely if this is the same source than if it's a different source of the DNA. So the DNA, if you will, what I usually call single source DNA, is the gold standard for understanding the likelihood ratio. As we go through the other types of evidence, it's good to know what the key features that made this work for DNA. Number one is the biology is well understood. So we know how to assign probabilities to the evidence. 2, there are population databases available. So we know how frequent the different alleles are. And 3, over the 40 years or so that people have been doing this, literature has been established that says this technology works and here's how it works, and the probability models work and here's how they work. And so there's a consensus on it. Important to note, of course, that what I usually say is single source DNA is the gold standard. We know that works, but there's still issues associated when there's not a lot of biological material at the crime scene. Then we can not always be quite as confident about the alleles, so there's some subjectivity there. And of course, there's been a lot of attention recently about mixtures and probabilistic genotyping. When you have mixtures of many people's DNA together at a crime scene, that can be very difficult to disentangle. So even there, it's not that the magic word DNA makes it all work. But for me, it's helpful to see how it works in blood type and DNA. So let me move to a second example. I think of DNA, as I said, as the good. The trace evidence is the bad. That's not right. It's not bad. It's a little more challenging. So the two examples I think about here are glass and bullet lead. And I've actually worked on bullet lead many years ago, but I'm going to talk more about glass here. So, and the data in this case, the evidence is glass fragments at the crime scene and at the suspect. And glass is a chemical, is composed of different chemicals. And so we can measure those chemicals and measure other characteristics of the glass. So goal would be, can we construct a likelihood ratio for evidence of this type, where the measurements are not categories or alleles, but continuous measurements? I'm going to argue that we could do this, and here's how. These are two pictures. The picture on the left is 49 measurements, 49 different fragments from a single glass source, and I've recorded the refractive index. And you can see there's some variability. even though they all came from the exact same glass source. I don't get the exact same measurement every time, but the numbers are very similar to each other. On the right is a distribution for 2,200 samples from 2,200 different glass sources. So in this right-hand histogram, each data point is the mean measurement for samples from a source. And so the source on the left has an average around 1.52, and so it shows up in the right over here. It's somewhat unusual. There aren't that many samples that have that as its refractive index. Most of the glass samples have refractive indexes over here, a little bit smaller. So can we get likelihood ratios from here? Well, I'm going to argue we can, and to do that, I'm going to show you the same pictures, but now put them on the same scale. What this picture shows me is there's very, very little variation among measurements of refractive index for fragments from a single source. And there's a lot of variability in refractive index measurements from different sources, which means if I have fragments from the crime scene and fragments from the suspect, I need to determine if they look more like taking two different samples from the picture on the left or two different samples from the picture on the right. Are they consistent with coming from one source, or do they look like they came from two different sources on the right? So fortunately, 18 years ago or so, a paper was published that shows how you could do this. And so just like we used X and Y to be blood types, here we're going to take Y to be refractive index measurements or aluminum concentration, and Y to be from the subject, and X to be from the crime scene. I kind of flipped them here. That is, for the blood type, I said, let's let Y be the crime scene and X be the suspect. But I did that for a reason. Here, the crime scene window, we know where those fragments came from. They're sitting there on the floor of the, right below the window. And so we know the X's, the source of the X's, but we don't know the source of the Y. It's true that the suspect has glass fragments on their sweater, but we don't know that they came from the crime scene. That's what we want to assess. So that's where the randomness is. To do this, we need to be able to make probability statements about Y. How do we do that? For blood type, we had distributions. For continuous measurements like refractive index, I need to find a distribution that explains this. Well, and it turns out that the normal distribution is often used for chemical concentrations or the logarithm of a chemical concentration. So there is a plausible probability model that we can use to decide how likely we are to get certain measurements. And what we can do is, under the same source hypothesis, X and Y are two sets of measurements from a single source from the same normal distribution. Under the different source hypothesis, X and Y are measurements from two different sources. They are measurements from two different normal distributions. And so Aitken and Lucy showed how you could do this calculation. I won't bore you with it today, but I will say what they basically did is built a model that says how much variability would we expect to see if they were coming from the same source? Not much. And how much variability would we expect to see between these two sources if they came from different glass sources? And the answer is much more. And their key findings, not a surprise, the likelihood ratio is small if Y and X are different. If the measurements don't match, if one is 1.52 and the other is 1.51, we can look at this picture and say 1.52 is very far from 1.51. They're very different sources. That would lead us to say these data are much more likely under the different source hypothesis. That couldn't happen under the same source hypothesis. But the likelihood ratio would be big if X and Y were very similar, and especially big if X and Y are similar and similar on an unusual value. just like if they're similar on an unusual blood type or similar on a rare allele. The evidence is strongest if the fragments match and they match on an unusual value. Aitken and Lucy did this for some glass samples and found likelihood ratios in the hundreds or thousands. So blood type gave us likelihood ratios around 2 or 20. DNA gave us likelihood ratios of 2 billion or 20 billion. And Aitken and Lucy found likelihood ratios for glass evidence in the hundreds and thousands. So we saw it work with categorical data. I just showed you that it could work for trace evidence. Why could it work here? Again, a well-defined set of measurements. We understand exactly what the evidence summaries are. We have probability models, maybe not quite as easy as in the genetic data, but we have probability models like a normal distribution that we can apply. And it's possible, although hard, to sample from the population and get a sense for how likely it is under the different source hypothesis. I will say the reason that I think of this as being different and harder than the DNA evidence is that the denominator probabilities, how likely am I to get a random matching glass sample, is much harder to make sure that you have a representative sample. And we'll also, towards the end of the session today, see that likelihood ratios can be very sensitive to the assumption that, for example, measurements have a normal distribution. So I thought before we go into the pattern evidence that I would have a Zoom question. So I need to spend a little time telling you what this question is. It is from pattern evidence, but it's resembles some of the things we've already seen. This is data that I did actually show you before, back on, I think, week 1, maybe week 2, maybe both. A study that was done in a thesis looking at known matches and known non-matches for 9mm bullet groove impressions. And the student did the microscopic analysis and recorded the number of consecutive matching stria, the largest number of consecutive matching stria that they observed for these 206 pairs of bullets. And so a reminder of how the table works, there were 146 pairs which were known matches. And in those 146 pairs, the examiner saw 55 instances in which there were the most matching stria they saw were 2, and then 54 where the most they saw were 3, and 1 sample where the 2 samples had 8 consecutive matching stria. The second row is for the known non-matches. There was fewer samples. I don't know why. It's just a data set that I found. And only 60. And in this case, 48 times was 2 the value, 11, 3, 4, 1. In the known non-matches, the student never saw 5, 6, 7, or 8 CMS. So here's the question that I'm going to ask. A forensic examiner in a case looking at 9mm bullet groove impressions from a question sample and a known sample, a bullet known to have come from a gun and then a suspect's gun, identifies the maximum CMS as 4. 4 is the evidence, if you will. Suppose this was the only data we had. It's not a lot of data, I agree. What would the likelihood ratio be in this case for comparing the same source hypothesis and the different source hypothesis? So I want to be quiet for a minute here and let you think about what these data are saying, and ask you to pick one of these and see, whether the likelihood ratio is making a little bit more sense to you. So thank you to the 33 who participated, as this really goes, it's going out on a ledge. And so the votes are in. People prefer the 3rd answer to the 4th answer. So let's go over that. Thank you for participating. So how do we think about this? The 3rd answer is actually correct. Why? We want to talk about the evidence in this case is the number of consecutive matching stria is 4. And we want to know how likely is it to get 4 if it's the same source pair. And so we're going to go from the known matches. And, notably, right, the AFTI theory of identification does a lot of talking about, think about those 2 populations. the known matches and known non-matches, right? I don't love the aptly theory identification, but it does draw attention to the right two populations. So first, let's talk about the known match population. How likely is a 4? Well, I saw 146 known match pairs, and 23 of them had a 4. It's pretty likely. About 16% of the time I get that. How likely is it to get a 4 in the non-match? Turns out not very likely. Only 1 out of 60 times did I get that. So that gives us the likely ratio of 9.5. The alternative approach, just to go back, the other answer took probabilities, but it didn't take the right probabilities. It took 23 out of 24 is among the 24 times that the students saw for CMS, how many were known matches and how many were known non-match. We don't want to think about the 4 as being the piece we fixed. We want to know how likely am I to see a 4. And so we have to make sure we think about which is both, and it is challenging because both things are known, right? When I compute one of these, I know the CMS is 4, and I know it's the same source example. That's what the 23 corresponds to. So the question that comes to mind, or is supposed to come to mind in the likelihood ratio, is I want to know how likely I am to get that 4 out of which population, out of the known match population. So anyway, that's the likelihood ratio. A couple of things to note. Again, this is just for these data. The statements I'm making here are not intended to be the definitive statements about how to analyze bullets. It's just from these data. If the CMS were 2, right, it comes up fairly often in both. It turns out in that case, it's slightly less likely in the top row and more likely in the bottom row. So 2 argues for a different source. For these data, 5, or for that matter, 6 or 8, would in fact be an infinite likelihood ratio. I've never seen that for a known non-match. Now, I don't believe that because this is not a lot of data. We need more data. But I hope it's a nice illustration. And in fact, it's a hope that it is a useful one for you to go back after the course and take a look at. So the last piece of what I want to talk about, there's a lot of time, but that's because it's a challenging piece, is pattern evidence. So many of the forensic disciplines focused on, that CSAFE is focused on, look at a sample from the crime scene, the question sample, if you will, and a sample from a source, a test sample from a source, the known sample. And we want to assess whether they are the same source or different source. Many examples. Here's some pictures. For most of these types of evidence, the data are really images. And so here you see images of a latent print on the left and a known print, a known exemplar next to it that may have been the source. And on the right, flipped, an impression on the right and the shoe that may have been the source of it on the left. And the question is, how can we assess these evidence? A number of challenges should be evident right away. And so that's why I think of this as the ugly side of likelihood ratios. Even figuring out what the evidence is challenging. I usually think of the evidence at the first level as being the images themselves. So I have the 2 fingerprint images or test impression from the shoe and the crime scene impression from the shoe. So, so we could try to say, how likely am I to see these 2 images? But that's going to be hard. And so often we now go in and say, okay, let's look at some features in those images or some data from those images. But that's the first hard thing is, what do we do with the evidence? Given the evidence, though, the questions are the same as the ones we asked for DNA and that we asked for the glass evidence. How much variation would we expect if these are 2 images from the same source? I give as an example, they won't be perfect matches because when a fingerprint gets deposited, there's going to be some distortion. But is the similarities outweigh whatever distortion I see? And then we also need to though think about, is the variation I'm seeing more like what I would expect if they were different? That is, could it be a coincidental match that it agrees on some features and not others? We won't spend time on it, but it's even more complicated than it appears on first blush, because there's also a lot of questions about manufacturing. How many shoes like this exist? How many bullets like this exist? Where are the bullets, right, that seem to have the same chemical concentrations? Lots of challenging issues. So we need to find these probabilities. Very hard problem. So I'm going to talk about 3 approaches for doing this very quickly. One is, let's try and apply the approach that we've used so far today. Let's figure out some summaries of the evidence and find the probability for those summaries or features. We can't assign probability to an image. There's too many possible images, right? But we can maybe do it for some features. The second thing I'm going to talk about, again briefly, is subjective likelihood ratios. And the third, I'll actually end up spending a little bit more time on, because it's the place where a lot of action is now happening, that I'll call score-based likelihood ratios. So here we go. The first approach is, let's try and build probability models for features. The top one is for latent prints from the work of Cedric Newman. So you have an image A, and let's measure as features the minutia. And for each minutia, we have the type of minutia, its location, and the tail here telling us the orientation of it. And then so this has 7 minutia. Newman also tried to characterize the constellation of minutia, using this geometric approach. And so he built up probabilities for type of minutia, orientation of minutia, and some of these geometric summaries of the minutia, and was able to generate some likelihood ratios. The second example that I have here is from a paper that I did with a student of mine that in between the time I made these slides up and today has now been accepted for publication. So here it says submitted, accepted, so we'll be coming out in Forensic Science International. We took blood stain patterns of 2 different types. CSAFE has published sample data sets of gunshot patterns and impact patterns. And we created 2 summaries. These are basically how variable, we take a blood stain pattern, we look at each of the droplets in the pattern and compute the angles, the impact angles and the orientation angles. And we compute summaries based on those angles. So how variable are the orientation angles and the impact angles? And we've got pictures here that say the likelihood ratio is color-coded here. Green is, now I have to make sure I know how we did this. Green is more likely under gunshot, and red is more likely under impact. And the picture shows squares for impact patterns, and that's the long football-shaped ellipse, and circles for gunshot patterns, and that's the circular ellipse. And the circles are errors that are being made. So I won't go into too more detail, but it's just a way of saying, here's people trying to come up with ways to talk about the probability of the evidence under these different hypotheses and comparing them. I'll leave that for now. You can pursue that. The second thing I wanted to talk very, very briefly about is the notion of a quote unquote subjective likelihood ratio. So there's some information here from the European guidelines for forensic interpretation. I'm not going to read them to you. You can read them as well as I can read them. But I draw your attention to the last bullet, which kind of says the probabilities that you need for a likelihood ratio ideally come from data, as we've been talking about today. But if not, the experience of the examiner might be used, or you might do a small survey like the thesis from the Oklahoma student about CMS. As long as there's some justification, you can do that. I don't think anybody really is a big fan of subjective putting in just, oh, this looks like a 90% probability under same source, So and 10% under a different source. And so I'll call the likelihood ratio 9. But that piece has certainly been people are very, very skeptical of it in the United States. So I'm not going to talk more about subjective likelihood ratios. I did want to show you, though, this scale that the NC guidelines have. If you come up with a likelihood ratio, hopefully from data, then given the challenges in understanding likelihood ratios, they have tried to create a verbal scale. And so, for example, the likelihood ratio of 500 falls in the middle here. They would say the likelihood ratio is 500. This provides moderately strong support for the same source hypothesis or proposition relative to the different source proposition. And if it were 1 over 500, they would say it the opposite way. It would provide moderately strong support for the different source proposition. But this is just one way of interpreting. The piece I'm going to end up saying a little bit more about is what we might call a score-based likelihood ratio. The idea behind the score-based likelihood ratio is to say, wow, the evidence is very complicated. It's this image with thousands of pixels, and I don't have a good way of assigning probability to thousands of pixels, but maybe I can come up with a one-number summary that takes the questioned image and the known image, puts them on top of each other, and computes a score that tells you how different they are. And so in this case, what I'd say we're doing is replacing the evidence E by the score D. Could be S, but it's D. So right now it's a different score. And CMS is something like that, right? CMS takes these two images under a microscope and computes a score. In that case, I think of it as a similarity score, right? A large CMS means the two impressions are very similar. And what the likelihood ratio idea now would say, as we did for the bullets, let's take some known matching pairs and see what the scores look like in those, and let's look at some known non-matching pairs and see what the scores look like there. So here the black curve shows you that these different scores D tend to be small in same source pairs, and they tend to be large, somewhere between 20 and 60, for known non-matching pairs. And we could use this as a one-dimensional summary of the very complicated evidence. And so to do that, what we would do is we would say, let's fit a distribution to these scores. And there are a lot of ways to do that. And let's get a score-based likelihood ratio. And so here I've said, suppose the different score was 10. The black bar tells us here, 10 is not uncommon for known matches. The red tells us 10 is pretty uncommon for known non-matches. And the ratio of the black height to the red height would be a score-based likelihood ratio. So how might that work? If there are latent print examiners here today, I'm sure there are some. FR stats is based on this likelihood ratio approach. The article that's written, it does something a little bit different, but this picture tells you how the data in FR stats could be used for likelihood ratio style analysis. I'm going to come back to this in a second, but this is a score that Henry Swafford and colleagues developed. The score for mated pairs is here, the lighter colored bars, and the score for the non-mated pairs is here. And so if we had a pair in this case, we would compute its score. It might come out to be 40, and we would say, gee, that's pretty common for mated pairs, but not for non-mated pairs. So that's how this can and is working. A couple of things to say about score-based likelihood ratios. There is some controversy. It tends to be relatively easy to figure out, to see the score distribution for known match pairs, but it turns out, at least I argue, the known non-match population is a little bit tricky. Is there a single non-match score distribution, like it seems in the picture I just showed you? Or should the non-match score distribution depend on some characteristic of the case? And if so, which characteristic? For fingerprints, seems like the number of minutiae should matter. Does the size of the print, physical size of the image that I'm working with matter? I don't know. Swafford does provide data on the number of minutia. So this is one of my favorite pictures in their article, because this shows you what the issue is. If you look at the same score distribution, the lighter histograms, it's pretty much between 0 and 75, almost for every number of minutia. You can see if you look closely, it's moving ever so slightly to the right. Right. So by the time I get to 15, some of the scores go up to 150. That's almost never happens down here. But the light curves are almost lined up perfectly. But notice how important the number of minutia is for the known non-match pairs. The darker curve moves as the number of minutia increases. It moves to the left. There's much greater separation at 15 minutia than there is at 5 minutia. And so the score-based likelihood ratio says, how likely am I to see a FR stat score of 40 under the same source hypothesis? And how likely am I to see it under the different source hypothesis? That answer clearly depends on the number of minutiae. So that's one challenge in doing scores. We have to figure out what are the important pieces to work with. Here's another score-based example that people have worked on. This is bullet lands. And so a group at Iowa State has done some of this work. The picture at the top here shows you profiles of bullet lands. So these are bullet lands are very smooth, but there are some gradations that come during the firing. And these are two different lands, land 5 from one bullet and land 1 from bullet 2. And we might want to know, do these match? Are these the same bullet? Again, you could try to build a model for all of the data, but what people have tended to do is to compute, say, consecutive matching stria, where each peak here is a stria. Or you could look at the correlation of these two curves, or you could look at the number of the average difference between the two curves. And so there are 7 measures that the Iowa State group looked at here. And the light blue are known matches, and the dark blue are known non-matches. What do you notice here? Well, one thing I notice is none of these are as well separated as the 15 minutia case here. So I could do this, but there's no one score that seems to work. I see there is a question. I will come back to it in a moment. So what they did is they said, in this case, no one score does a good job, but I have lots of scores. Maybe I can combine them. And they did. They used a pretty fancy statistical technique known as a random forest and a bunch of training data. And what they did is they took the 7 scores for a bunch of pairs of matches, some known matches, some known non-matches, and they built a machine, artificial intelligence, if you will, machine learning, if you will, statistical model, if you will, that gives you, for these 7 scores, the probability of that it comes from a matching pair is, they estimate that probability. And that's their single summary score S. So the summary score in this case took a lot of work to develop. You don't get it just by looking at the bullets. You have to train up a model to tell it to you. But the model spits out for any pair that you can pull a bullet lens you put in, a score S, which is an estimated probability of a match. And look how well this has worked for these sample data. The scores are along the horizontal axis from 0 to 1. And for known matches, all of the scores are bigger than 0.5. And for known non-matches, all the scores are below 0.25. So this score perfectly separates the two populations and does a great job. So that's an example. I don't necessarily think of this as a score-based likelihood ratio. I think of this almost as a score-based two-stage approach. That is, here's a score, and you can use that score to try and determine whether they match or not. But you can do a likelihood ratio analysis as well. So that's a way of combining multiple scores. And this just says what I said. This, you can use those score distributions for likelihood ratio, or you can kind of choose a threshold and try and do it that way. I'm not going to belabor that now because I want to make sure we have time to discuss the questions. So I'm going to pause here, read the questions. Stephanie asks, could you use the distribution of glass refractive index measurements similar to the matches distribution? What's the probability of finding a refractive index in the general population of non-matching glass? Interesting. So Stephanie's asking, if we go back to the glass, is there an alternative to the approach that I laid out for glass? What I said we should do for glass is think about it as two separate populations: crime scene sample, suspect sample. And let's see how, whether the evidence that we have, these set of glass measurements from crime scene sample, set of crime measurements from suspect sample, how likely are we to get those under two hypotheses? And Stephanie, I'm going to dismiss that for now, and I'm going to apologize. You can get whiplash as I go back to the glass pictures. So we come back to slide 62 in a moment. But so as we go back way back here, if we were confident about these between measurements, that this was the distribution of, just to be specific, let's say car window glass, that this completely characterized the car window glass. And Stephanie's asking, can I do more of a likelihood ratio by just looking at this distribution? And unfortunately, the answer is no, because the question we have to ask for the likelihood ratio, whether it's score-based or any other way, is what's the probability of seeing the evidence that I got under these two hypotheses? And so the picture on the right can only really tell us what's the probability of seeing a glass sample with a particular refractive index. And the evidence in our case is two glass samples. And so the challenge in the glass case is I need to know both of these types of information. That is, I need to know how similar the fragments within a single source will be. We know this to be true now because I've shown you the data, but you can imagine for some other things, and for example, bullet lead, that there might be more variation within that of bullet lead. And so within a box of bullets, there may be more variation within than there is for the glass. And that needs to be taken into account to make the judgment. I don't feel like I'm giving a terribly clear answer to your question. I apologize for that. So maybe I'll come back to it. So one more try for Stephanie is, so for me, what I think you're describing is a little bit more of the two-stage approach. That is, if I see these two matching types of glass fragments, you can do what I think you're asking, which is now I can look at the between and get a sense for how probative that is, how likely that, how unusual that value is. And if you were here last week, we discussed the importance of doing that. That is, first thing we look for is, do the glass fragments appear to be the same in terms of their refractive index? And then we ask that second question, which is like the denominator of the likelihood ratio. How likely am I to get it under the different source hypothesis? I'll have to leave that there with apologies if that was not clear. An anonymous attendee asked, how do you know if a score is good or bad? What does the score mean in the random forest approach? So that's a great question. That brings us back to slide 60, whatever. So the scores mean different things, right? So we'll start here with Henry Swafford's FR stats. The score here, it as a number is not so easy to describe, but it is summed up over the minutia, combining a measure of how closely aligned the two minutiae are in the print, the distance, how closely their orientations are aligned. And Henry and team developed a way of saying, if you're close, this is not what they did, but for simplicity, I'll describe it this way. If you're really close, you get 5 points. If you're kind of close, you get 4 points. And right, you can think about it that way. So they came up with a score that will be high if the images look the same, and will be low. They have negative points for certain things too, right, if you don't agree. And so in that case, a high score just means consistency. In the bullet-led case, as I said, there are scores here, each has their own interpretation. This first figure is the number of consecutive matching stria. That's one we all know how to interpret. The more consecutive matching stria, that's more likely under a known match, the light blue. The curve here is a score that looks at these two curves, computes the difference at each bar along the way, and sums up the absolute value of the differences. That's now a different score. A small score suggests same bullet, a large score, different bullet, right? So any score you can interpret it has its own meaning. And then the distributions are the data that tell us how likely a score is under the same source and different source hypothesis. That's why we need to have known matches and known non-matches in these cases. And then your last piece of your question, which is, what was the score here? As I said, in this case, the score is a little more complicated because it's a score of scores, if you will. They take the 7 scores that they could compute for a pair, and they built a statistical model. And the statistical model spits out an estimate, a final score between 0 and 1, which you can just think about as a measure of similarity. It purports to be an estimate of the probability that they match, but that doesn't have to be true. It can also just be thought of as a measure of similarity. So, short answer, scores are developed by researchers in the field to characterize some features of the data, and they each one has its own interpretation. Most important to know is, is this measuring similarity, in which case a high score suggests same source, or is it measuring a difference, in which case high scores mean different source? Thank you for those questions. I will go on with a few final comments about likelihood ratios. The likelihood ratio have been critiqued for a variety of reasons. One powerful one was by Lund and Iyer, who noted that given the same data, different statistical models give different likelihood ratios. And so this is a picture from their paper, which I really like. I told you that when I looked at the GLASS data, we looked at assuming a normal distribution. They did that as well, but they looked at a bunch of different normal distributions, normals with different variances, if you will. And they found that gave you some variability, although not too much. The likelihood ratio for the sample was around 1,000. When they did their analysis, changing the normal distribution a little could make it as small as 100 or as big as 2,000. This is a hard scale to read because it's what's called a logarithmic scale. 500 is not halfway between 1 and 1,000 on this scale. 500 is much closer to 1,000 on this scale. So it's a little bit hard to read, but you get the idea. And then they said, well, you assume normal, but what if I don't assume normal? If I just assume some symmetric distribution that could be any shape, doesn't have to be bell-shaped. And then you'll notice the red bar gets longer, which is for some symmetric distributions, the likelihood ratio gets closer to about 30. That's the lower end of this bar, or it goes up to about 5,000. So I'm much less sure now. And the bottom is if they said, we're going to allow pretty much any distribution in the world, as long as it's somewhat close to the data. And now notice what happened. It's possible that they could find a distribution such that the likelihood ratio flips from being 1,000 to below 1, that the same data now suggest different source. So they were very concerned about this. I'm a little less concerned for reasons that I will share in the next 10 minutes or so. But the one statistical critique I've made of this is they were, in my view, very generous in defining what are other plausible models. So that is, their red bar includes things that I probably would not include as being consistent with the data. So I think they overstate the challenge here. But I know Steve and Harry, and they're very smart. And so this is an important note, the sensitivity issue. Also worth noting, other challenges in other places where people have criticized the likelihood ratio is there are a lot of issues that go into assessing the evidence for pattern evidence and trace evidence that are not automatically accounted for in a likelihood ratio. When you look at sneakers and you're trying to assess sneakers and how likely a match is, you want to take into account that there are a lot more size 9s than size 22 people in the world. And so if you have matching size 22s, and you also need to take a little bit of account of how long sneakers last. That is, things that expire quickly have different characteristics than things that last a long time. When we looked at bullets many years ago, the packaging of bullets into boxes complicated things. You could have bullets that were manufactured at different times showing up in the same box, which increases the chance of a coincidentally agreeing measurements. So very challenging to develop. A lot of good work going on to try and get there, mostly in the score-based approach that we've talked about. So here's a last Zoom question of the day and of the course, a little facetious, but here's which of the statements of likelihood ratios based on the last hour and change, summarize what you now think about likelihood ratios. And a lot of people, again, thank you for participating. A lot of people identify 1 and 5. Others agree with 3. And 2 and 4 are very few, much fewer. So, and here we go. And I liked the answers that you gave. Likelihood ratios provide a continuous measure of strength of the evidence. For me, that's a positive. It doesn't require a binary match decision. Likelihood ratios are the greatest invention since sliced bread. Only a couple of people said that here. And just so you know, I'm not allowed to answer, so it wasn't me. And the third item says, likelihood ratio is intriguing, but difficult to apply for pattern evidence, which I think is true. Only statisticians are interested in likelihood ratio. I was pleased to see that people did not say that. And then people noted, as in the 2 slides ago or 3 slides ago, likelihood ratios can be sensitive to the assumptions made. The last thing I thought I would do, so thank you for participating, is summarize the likelihood ratio, relate it to the other approaches we've discussed, and conclude the workshop. And we should have time for additional questions if people have any. Advantages of the likelihood ratio. It explicitly addresses the 2 relevant hypotheses, can do more than 2, but the 2 typical hypotheses in the pattern world, same source, different source. So those are being addressed simultaneously. Provides a quantitative summary of the evidence, as we just discussed. It requires us, or it should require us, to make our assumptions explicit. So we'll see in a second, a disadvantage is that it's sensitive to assumptions, but a positive is the assumptions are on the table. So they can be questioned, which is harder to do if it's just, I looked at it and I said X, right? So we should, at some level, value the fact that the assumptions are being made and put on the table. As I said, no match, non-match decisions. The likelihood ratio is complicated with software pattern evidence. can even get more complicated if we try to take into account some of these other factors, like putting bullets into boxes or trying to account for the transfer of fibers during the commission of a crime. But it can be done. And it can even be done, I don't think we'll necessarily ever get there, to combine different sources of evidence. That is, you can say, what's the likely ratio given this blood evidence and this firearms evidence and this blood stain pattern evidence, and try and put them into one giant likelihood ratio. We're having a hard enough time doing that for one piece of evidence. But there are disadvantages. It requires very explicit assumptions about how likely different values are. And as we saw, the likely ratio can be quite sensitive to those. Another challenge in the United States is, the likely ratio is often framed as how likely the evidence under the prosecution hypothesis and how likely the evidence under the defense hypothesis. But of course, in the US, the defense does not have to provide a specific alternative. And so we end up using pretty generic alternatives of someone else in the world left this evidence or something like that. For me, the most challenging part about the likely ratio in the work that I've done is the need to figure out a representative distribution of values for the different source world. So when we worked in the bloodstain example, I gave you only 30 seconds on that today. My student and I, we had a data set with 60 firearms examples and 60 impact examples generated from a single experimental setup in a lab. That's not going to be representative of all the kinds of impact blood patterns that one might find if you go out into the real world. And how do we get that more representative data is a challenge. And the last challenge, disadvantage, I'll say, is as we saw today, the likelihood ratio can be a little confusing. And that's for us who are kind of spending 8 hours trying to get a handle on it. Can imagine it being even trickier for a lay jury member who's coming in and being exposed to it in the course of a trial, having never seen any statistics or workshop before. So that's a real challenge that people are working on. How do we convey this information? So I thought before I close, I wanted to put some of the ideas that we've talked about over the last few weeks together. So first, let's think about expert opinion and the likelihood ratio. We talked 2 weeks ago about black box studies, and they provide field level data about error rates. One of the ways I like to think about black box studies is the following. Let's think about a black box study this way. Let's take the evidence in the case, the latent print and the known exemplar, and let's forget about the minutia and the distortion. Let's replace the evidence in this case by what the expert said. What did the examiner say? The examiner said ident or exclude or inconclusive. And we have data about this from the black box studies. So if you focus in on the middle here from the Ullery paper, if an examiner says ident, the data from the black box study says the probability of getting an ident from known matching pairs is 3,600 divided by 6,000, or around 60%. The probability of getting an ident from a known non-match is 6 out of 4,000, right? So about 1 in 1,000. And if you take that ratio, it turns out to be 418. So the evidence has changed. The evidence now is the examiner says ident. When the examiner says ident, that's strong evidence in favor of the same source hypothesis. But now it's not I know it's a match, it's a 400, right? So I know how to compare it to other types of evidence. And we can do the same thing for the exclude. Interestingly enough, it turns out when you get an exclude, because there were many more false negatives in the Ullery paper, the likely ratio is 0.085. And so if the evidence is the examiner excluded, that turns out to be a likelihood ratio of 12 in favor of the different source hypothesis. And I've been in a recent email exchange with an attorney about the Monson et al. Firearms black box study data, the Ames 2. and found this very interesting. If you look at the 5 categories they reported on, identification, elimination, inconclusive A, which is lots of matching features, but I don't call it an ident, inconclusive B, real inconclusive, inconclusive C, I see differences, but I'm not prepared to eliminate. The likelihood ratios turn out to be, to me, very interesting. The ident, not quite as strong as fingerprints, but very strong. If an examiner says ident, likelihood ratio is more than 100. So strong support for the same source. Elimination, incredibly similar to the exclude for fingerprints. So about 12 in favor of different source. But the 3 different inconclusive types I found fascinating. And there's been a lot of controversy about inconclusives in these firearm studies because in the non-matching case, there are a lot of inconclusives. Look at the inconclusive C. When the examiner sees differences but is not prepared to call it an elimination, that statement is in itself evidence in favor of different source. And so I found this interesting anyway. Hope you do as well. So that's how I think about putting together the likelihood ratio ideas that we discussed today and the expert opinion idea that we talked about 2 weeks ago. Penultimate slide for the course. We can think about the 2-stage approach in the likelihood ratio also. Stage 1 of the 2-stage approach determines whether the 2 samples are indistinguishable. And one way about combining these 2 notions is we can say, let's think about the evidence E not being the measurements anymore, but being the fact that the examiner has decided the observations are indistinguishable. So that's the evidence now. And the likelihood ratio would tell us to say, what's the probability that the glass examiner is going to say observations are indistinguishable if they come from the same source? And what's the probability they're going to say observations are indistinguishable if they come from a different source? It turns out that the first of those, the probability that the examiner says they're indistinguishable, given that they're same source, that's usually pretty high. And in fact, it depends on the statistical approach that we use. So if we do a t-test, which we talked about last week, I can tell you that probability. If I use a 0.05 cutoff for the p-value, this will be 0.95. That is, if I have indistinguishable samples and I use a statistical test in my exam, then the probability I'll say indistinguishable is 0.95. The hard part is trying to get stage 2. What's the probability that I'll say indistinguishable if they come from different sources? And that's exactly what stage 2 tells us to compute the coincidental, quote unquote, match probability. So you can see one of the reasons I like the likelihood ratio, I find it a unifying theme. I find it the right way to think about evidence. How likely you see the evidence under the same source hypothesis? How likely you see the evidence under the different source hypothesis? And if we are flexible in what we think the evidence is, it covers everything we covered in the course. So my summary of the short course, you will have your own. I'm grateful to those who've been here, which I think is most people, for the full 8 hours. That's a huge investment. I hope it was valuable. I hope I've explained why probability statistics concepts are so crucial to thinking about evidence. We covered the basics of probability and statistics, and we discussed statistical considerations relevant to current practice. So expert opinion and black box studies. And we reviewed 2 more quantitative approaches, the 2-stage approach based on testing and the likelihood ratio approach today. And the key points for me, if you were going to take 3 things away from this short course, it would be any approach that you use should be looking at the 2 hypotheses. So it's not okay to say the glass is indistinguishable. We have to say, how likely is it that the glass is indistinguishable under same source? How likely is it the glass is indistinguishable under different source? We need to be explicit on where what data we have to support the statements we're making about the strength of the evidence. If it's a quantitative approach, we should show the data and assumptions. If it's expert opinion, we should maybe be showing the images and how we know how much weight to give them. And we should accept that there's a level of uncertainty associated with a conclusion. This says we need to describe the level of certainty. It's probably better said as we should be prepared to describe the uncertainty associated with a conclusion. Last thing I would like to say, or two last things, I said it once already, but I'll say it again, thank you for your participation in the course. But the very last thing I want to say is, Anthony will be sending an evaluation out. We've done that for the last 3 weeks. Incredibly valuable to me. This course has undergone a huge change based on feedback that said, 3 sessions of 2 hours is too quick, and we should slow it down. And in doing so, it made me totally rethink how to lay out the material. So I'm extremely interested in knowing how you feel about the way the material was laid out over the 4 weeks. When you do the 4th session evaluation, if you have been in all of them and want to comment on the course, that would be welcome as well. So, I'm done there. Look forward, hopefully someday, to seeing or meeting some of you in person at a IAI or other meeting. Anthony, I will turn it back to you for our close.
Thank you, Hal, for taking the time today to run through likelihood ratios, but also for all of your time in these 4 sessions. Thank you all for joining us. We hope you have a great day.